Swayam Prabha. Digital India. Educated India.
Welcome to week 2 of the course on Muffler Acoustics. The first lecture of this week, we will basically resume our discussion from where we left in the last week's lecture. In this today's lecture, we are going to focus on planar waves that propagate in ducts which carry mean flow. That is one dimensional wave propagation in ducts, but now including the convective effects of mean flow in the ducts. As you can see from this figure, you have a duct and say u naught is the uniform flow velocity. In ducts it is never actually uniform flow, it is actually more like a plug flow, something like this, but we approximate that as a uniform mean flow. And what we are interested particularly is that let us say for mean flow u naught, which is much less than the sound speed, that is the Mach number m naught, which is given by u naught by c, is much less than 1. Typically, we consider in automobiles we rarely exceed 0.1, 0.15 perhaps at the max, 0.15 Mach number. So, we will be happy, we will be contented with designing systems or analyzing wave propagation with maybe maximum of Mach number 0.15 or something like that. So, we are going to develop the basic theory underpinning wave propagation, planar waves with mean flow effects. So, that is going to be the focus of this lecture. So, let us develop the maths. If you recall the last week's lectures, we first talked about the continuity equation. And so, what was that? Rho t plus rho u x is equal to 0. Of course, you consider a small differential element and end up with this. So, analysis remains the same other than the fact that rho now is rho naught plus rho tilde, and p, of course, we have not come across p here, but this ambient pressure, I am sorry, plus p tilde, and u now is u naught plus u. Particularly if we substitute this in here, what we get? Rho naught plus rho t plus rho naught plus rho u naught plus u, and whole is differentiated with respect to x equals 0. So, now the analysis is pretty much the same. Let us number this as equation 1, and on substituting all this and simplifying, expanding out, I am sorry, we end up with this thing. So, obviously, like in the previous class, we saw the temporal changes of density is 0. So, this then simplifies to your P t, where this thing obviously would mean del t, and this would mean del x. Okay. So, and then term by term we need to expand out the things that are in this thing, rho naught u naught plus rho naught u tilde plus rho tilde u naught plus the second order terms which you definitely can ignore, but probably just wait for a while. And now we are assuming the flow is uniform along the axis of the duct, that is along, this is the x direction, I am sorry, forgot to mention. So, u naught, that means the flow is fully developed, actually it is a uniform flow. So, it's by definition it is uniform across space, and we also get, so that would, and density is obviously constant with space. So, here you get something like this, and then rho tilde and u x and u naught plus rho u x is equal to 0. So, that is what we are going to get. Obviously, this term then goes away, and what we are really left with, this term is also a second order term. This is a second order term, while this is a 0th order term. This is a second order term, because rho tilde and u tilde is small, their products are also smaller. So, we will probably ignore this term and ultimately retain only the following terms: rho naught u x plus rho tilde x into u naught is 0. So, this is what we are going to get. Let me write down this equation in a more cleaner manner perhaps on the next slide, which is rho tilde t plus rho naught u x plus rho tilde x u naught is equal to 0. Let me name this as equation number 2. Now, as a check of self consistency, it is important that we should be able to get perturbed continuity equation pertaining to 0 mean flow from equation 2. How do we get that? If you simply substitute u naught equal to 0, that is to say, if you put u naught as 0, that is a stationary medium, what would you get? You will get that is your old familiar equation for the continuity one. So, let us call this 2 b and this is 2 a. This is if you have this condition, but in the more general case, when you have a non-zero uniform mean flow, equation 2 a will apply. Now, let us focus our discussion on the momentum equation. Momentum equation. So, we recall again here that rho into u t plus u into u x plus p x is equal to 0. This we saw from our last week's course, last week's lectures. Now, again we pretty much do the same thing, that is to say, we have the same perturbation quantities rho naught plus rho tilde, p naught plus p tilde, u naught plus u tilde. So, now is the time where we substitute the pressure one in this one. So, when we do that, we would eventually end up with this thing. So, I am dropping out the thing like u, I am already simplifying this. So, I am directly writing it as u tilde and t plus u naught plus u tilde and u naught plus u tilde x. P x is equal to 0, with the understanding that ambient pressure, atmospheric pressure does not change with space, it is constant. Now, what do we do after this? We should probably simplify the terms, and once we do that, we are going to get u tilde plus rho tilde u tilde t. Now, we have this term, it can, the simplification can get a little tedious. So, well, in order to keep the interest going, I would assume certain simplifications, you can work it out on your own. So, I will underline the second order terms, which you by now should notice that this is definitely a second order term. So, I will probably not carry forward this thing in the next step. Rho tilde u and rho naught u naught, rho naught u tilde, rho tilde u naught, so the whole thing needs differentiation so sorry, here you have your this thing, not the whole thing. Well, so well, we get this, and this term of course wouldn't survive this one u naught, because once you differentiate with respect to x, this is not there. So, eventually you will end up with only u tilde x, and I would get this thing here. Now, what we get is rho naught u tilde t, rho naught u naught u tilde x, that comes from here, plus rho naught u tilde and u tilde x. So, this is clearly a second order term coming up for us, rho tilde and u naught, and again you have your this thing, and rho tilde u tilde u x, and plus you get your. Let us identify the second order terms. You have your, this is definitely a second order term, and so is this. So, this is what we are getting for now, but we also see that rho tilde and u tilde x, this is also there. So, this term would also drop out, eventually leaving us with only the following, which may also be written in a more succinct manner, the following form. Look, eventually whatever we do as a check of self consistency, it should boil down to the state when you do not have mean flow. So, this, let me name this as equation 3, and clearly when u is 0, if u is 0, you get back your familiar momentum equation, that is rho naught into u tilde t plus p tilde x is equal to 0. So, that is your Euler equation, linearized Euler equation, momentum equation along the x direction. So, we have equation 3 and we have our equation 2a, is not it? That is your continuity equation with mean flow, and equation 2a, and your equation 3 is your momentum equation with mean flow. So, the idea then is to combine equation 2a and 3. So, let me write down both these equations, rho tilde t plus is equal to 0. Here you are, rho tilde x, and your other equation that we just derived right now was rho naught times u t plus u naught u x equals 0. So, other than these two equations, it is important to also recall that we have the isentropicity relation is coming from the equation of state for a lossless fluid, which is what we are really considering. So, we have this. What we need to do is that use this equation 4 in the above equations. So, once we put this particular relation, isentropicity relation, in here, what do we get? We get c square plus rho naught u x plus u naught by c naught square and p x. equals 0. All right. This is what we are going to get, but of course, we need to simplify this thing further. So, we multiply all throughout by C square to end up with rho naught C naught square times u x equals 0. This is what we are going to get. Let us name this as equation number 5, and what about this one, momentum equation? You also have this. So, we have successfully eliminated the acoustic density variable rho tilde, and the equations that we have got this particular equation, this one, and we have also got this equation, momentum equation with mean flow and acoustic quantities P tilde and U tilde, and the continuity equation in which we have only the acoustic pressure variable. Our job is to combine equation 5 as well as this equation. How do we go about doing so? So, what we will probably do is that we will differentiate this equation mark star, which is the same as the previous one, with respect to x. We will differentiate this equation with respect to x. So, what will we get? We will get u t x plus u naught into u x, actually u tilde, and we will get x x plus p tilde x x equals 0, is not it? Everything else is the same, it is just that you keep on putting u 0, u naught 0, and you retain, you get back the stationary medium thing. So, this is, we will keep this aside for the time being and worry about the continuity equation. So, for this equation we will basically differentiate with respect to the time t. So, we get T t plus u naught p tilde x t rho naught C naught square u x t equals 0. So, we have got this equation 6 and equation 7. Now, what? How do we go about processing these equations further? That is the job. So, what I suggest is that let us open the bracket in this one and let us multiply throughout by rho naught. So, here you are, and we probably, what we could do is that we could subtract these two. So, this is obviously u tilde, and I forgot to remove the thing here, x here. What do we do now? So, what we could do is probably divide equation 7 throughout by C naught square, and here you also have C naught square. So, this will go away and you will just have your rho naught. Okay. And then we clearly see that if we subtract 7 from 6 or vice versa, this particular term that I will just encircle this one, u tilde x t or u tilde t x, whatever it is, that can just cancel, or we can sort of eliminate that term. So, I will say subtracting 7 from 6, we get, what do we get? We get rho naught u naught u x x plus p tilde x x and minus 1 by C naught square p tilde t t and minus u naught by C naught square p tilde x t. So, this is what it is, equals to 0. So, we are nearly there, we are almost there, apart from a few things that we further need to do. And what is that? So, now this thing should be clear. We only have a term, this one, the first term which involves this u term here, where acoustic particle velocity, I am sorry, should be written as u tilde, which needs to be eliminated. So, how do we do that? Actually, before we do that, let me write this in a more, in a form which is, we are probably a little bit more comfortable. U naught by C naught is m naught, you get this, and you further get 1 by C naught P tilde x t minus 1 minus C naught square P tilde t t plus rho naught u naught u tilde x x equals 0. Now, I guess this is probably equation number, let me call it equation number 8, and we need to eliminate u tilde x x, like I said. So, what is u tilde x x? If we go back to our continuity equation, that is your this particular equation, equation 2a, we can probably write this as 1 by C naught square P tilde t plus P tilde x by C naught square u naught is equal to minus rho naught u tilde x. So, this is what we get, and so, the end result is that we will be getting things like this. So, I am just calling equation 9 because we have got equation 8 out there. Let us substitute equation 9 in the last equation 8, we just need to differentiate again with respect to x. So, I would probably do it somewhere here itself. So, once we differentiate with respect to x, so we get x x and x t, I mean T x. So, let us directly substitute equation 9 in equation 8. Substituting equation 9 in equation 8, we get, what do we get? P x x minus m naught C naught plus rho naught u naught, and we will get rho naught C naught square, and there will be minus. So, plus into minus is minus. So, there will be minus sign here, and P tilde t plus u naught P tilde x equals 0. So, we are on our way. So, we are definitely on our way. You see u naught by C naught. So, that is your m naught minus m naught by C naught times P tilde t. Actually, it will be, I am sorry, I made a mistake here, it will be x x. So, x, and you have your u naught and P tilde x x equals 0. So, the after lots and lots of algebra, we are getting something in terms of the acoustic perturbation pressure P tilde. So, we can clearly see this term here, the one that I have underlined in orange, and similarly here. So, these terms are something that will add up. So, you will get minus 2 m naught by C naught P tilde x t, and then you also have this term. Let us see how things shape up. So, we get P tilde x x minus 2 m naught by C naught P tilde x t and minus P tilde t t by C naught square, and you also have your this term minus m naught into m naught, because u naught by C naught, and you have plus minus. So, you will get minus 2 minus P tilde x x equals 0, is not it? That is what you are going to get. So, we will take this term and this term together, we will combine them to get your 1 minus m naught square times P tilde x x and minus 2 m naught by C naught P tilde x t and minus P t t by C naught square equals 0, but I guess things are fine here. Let us check it out if things are correct, at least from the dimensionality point of view. This of course is dimensionless, 1 minus m naught square. This has pressure differentiated twice with respect to the spatial variable x, and this is dimensionless, but you have your pressure and you have your second. So, basically pressure differentiated with respect to x, and then you also have your plus, you will have your somewhere you will have your second, but here in the denominator you have meter per second. So, this thing will go away, second. So, you are still good here because dimensionality wise it is fine, and here you have your PTT. So, your meter per second square will cancel here. So, I guess we are fine, we are doing good in terms of maintaining the dimensionality of each term, and yes, and another way of course is to write this equation in terms of your velocity, absolute velocity rather than non dimensional velocity. So, that we recognize m naught is u naught by C naught. So, we do that and multiply throughout by C naught square u naught P tilde x t minus P t t by C naught square is equal to 0, and if we multiply throughout by minus sign. So, let us see what we get. We get your u naught square minus C naught square times P x x plus 2 u naught times x t and plus. So, I guess we are there what we promised to derive, but before we end, we probably it is a good idea to talk about check self consistency things. If you put m naught is 0 in the equation number 10, it is just P tilde x x minus P t t C naught square. So, that is your wave equation, the one that was covered in the last week. So, that is your wave equation, second order hyperbolic wave equation for a stationary medium, and if you insist time harmonicity, what are we going to get? We are going to get the Helmholtz equation, one dimensional Helmholtz equation. Similarly, it is very easy to see if you put u naught is 0 here, that is in this term. So, this term will obviously go away, so will this, and you will just end up with your same thing. This should not be here. Okay. So, if you put u naught 0 here, you will just get this term, and we will just have this. So, it is pretty much the same thing. So, purely from the point of self consistency, it is doing good. So, equations 10 and 11 then are basically your equations for the one dimensional wave propagation in ducts carrying uniform mean flow. To derive the solution of this equation, we are going to do some algebraic manipulations that will begin the next lecture with the solution of one dimensional wave equation including convective mean flow effects, that is a solution of equation 10 or 11 equivalently, and then talk about each term, whether it is the waves that propagates in the forward direction and the wave that goes in the negative x direction. So, yes, so I guess we will stop here. Thanks for attending and stay tuned for the next lecture.